Good. Thank you very much. There's the speakers. And all the best for Dragonfly, of course. Okay, so the next speaker, we welcome Carol Mundell from the European Space Agency, our Director of Science. She's connected and she will present the slides from her computer, if I understand correctly. So Carol, if you are connected, the floor.
Good morning, colleagues, if you can hear me, if I'm coming through clearly. Can you hear me? Yeah.
Yes, it's
great.
Okay.
Thank you. Okay. Am I sharing the screen? Unfortunately, when I share the screen, I can't see any of you, so I'm hoping that all is well.
Okay, so you can start when you want. I will just give you the title of your talk, From Near Earth to the Fabric of Space-Time. So thank you for your talk, Carol.
Thank you very much, Olivier, and it's a great pleasure to join you all here today. And when Athena kindly asked me to give a presentation to you, she said, maybe you could talk about the solar system. And so I started to look through all of our missions. I've been Director of Science now at ESA for just 2.5 years. And I realized that there's actually solar system in just about everything we do. But actually for the European Space Agency, this year is a milestone year. We're celebrating our 50th anniversary. And we are unique as a space agency, as the world's only intergovernmental space agency. So we bring together now 23 member states. We were founded with 11 member states. And actually, yeah.
Yes, you need to share. I think it's okay now.
Is it okay? Is it coming through?
Very good. Thank you.
Yeah, okay. There's a little bit of delay on the line, perhaps. And in fact, when the agency was first formed 50 years ago, from the formation of the merger of the European Launch Organization with the European Space Research Organization, it was very clear that those pioneering founding fathers put science at the heart of the agency, and they encapsulated that by actually making science a mandatory program. And that means that each of our member states must contribute to the program, and that gives us the long-term sustainable guarantee that we can develop missions, particularly things like our solar system missions, that need that long-term sustainable funding, whatever the political climate is. And you can imagine managing 23 countries' priorities and political systems. That stability is vital for the science program. And in fact, since then, obviously, the agency has grown dramatically, and we now have a very comprehensive agency that delivers across a wide range of areas. But I think really at the heart of that, the backbone really is the science mandatory program. And I've obviously, is celebrating today, I've put the movie of ESA's Huygens probe landing, still humanity's most distant ever landing on a distant solar system, and in fact the most distant moon. And I think it's difficult to state, strongly enough how important that work was then. And I know the celebration that we had in January, listening to some of the instrument PIs. Now, of course, we look back 20 years, it's a great achievement, but actually the excitement, the uncertainty, and really the wondering what was going to happen. So I think it was a hugely pioneering mission. The European Space Agency Science Programme objective really is to enable European leadership in frontier breakthrough science and technology, and to empower our member states to lead in global space science. And of course, we do that also in collaboration with our international partners, which is why I think the meeting today here is so exciting. And really, over the years, we have delivered, sometimes with really very limited budgets, some very iconic missions. The program is very competitive. It's built bottom up. From the proposals from our science community, we develop overarching strategies, but each of these missions will have gone through a very rigorous selection. And for a medium class mission, something like Rosetta, it will have gone through probably maybe 30-1 oversubscribed on the initial proposal. And then there is a competition across all of our 23 member states for the industrial contracts. So it always means that there are many disappointed communities who don't get selected, but actually when a mission comes through, we know it's going to be groundbreaking. And of course, the ESA mandatory program pays for the spacecraft and the operations, but it's the member states who provide the payload. And that continues to drive the innovation within the universities, the research institutes, and the science community really at the forefront. And I think the solar system missions in particular encapsulate that sense of collaboration, of frontier spirit, sometimes risk-taking. And of course, I think, John Zarnecki, you're in the audience. I remember you saying in January your disappointment at not having a mission selected, and you went away and reformed your team to actually successfully win a slot of the payload on the Huygens descent probe. So again, that constant innovation within our communities. And our missions, nominally, they may be designed to fly for 3, 4, 5 years, but some of them go on for many, many years. So again, there's innovation in the operations. You can see SOHO that we operate in collaboration with our NASA colleagues, launched in 1995, still providing iconic frontier science. And of course, there are 2 reasons we go to space. First of all, we go to space to go to places. After, our obviously the successful Cassini-Huygens, ESA then led the phenomenal Rosetta mission, landing the Philae lander on a comet. And then now we're developing the sister mission to that, Comet Interceptor. But also we go into space so that we can study the cosmos, places that we can't ever hope to go to, distant stars, galaxies, and ultimately the edge of the known universe and the fabric of space-time. XMM Newton launched in 1999, still going strong, teaching us about the hottest components in the universe. And of course, Mars Express has been orbiting Mars and giving us brand new views of that planet, which again, we share those data with our international collaborators for future missions and future ambitions on Mars. Our Planck satellite, of course, was launched in 2009. It's now been retired. It has given us the most detailed map of the cosmic microwave background and really the total census of the universe, baryonic matter, and dark energy. And in fact, we had an archive fellow, a young woman who wrote a proposal to come to ESAC here in Madrid. And she said, I'd like to use the Planck data because I believe I can find all the metal asteroids embedded in the data. So again, new generations of scientists coming along and looking at missions that provided wonderful data that we curate in our archives, but for which we use in entirely different ways when new scientists come along with new ideas. So again, building up this legacy. And you can see some of these incredible missions that we have in development, flying or retired. Again, with our collaborators at NASA, James Webb Space Telescope, again, is transforming our views of the distant universe, but also the solar system. And it's been a fantastic collaboration, providing some of the iconic instruments on James Webb from our European science community, supported through ESA. And of course, the exquisite launch of the Ariane rocket on Christmas Day of 2021 that took James Webb into the sky. We have an exciting year coming up. The SMILE mission, which is in collaboration between ESA and the Chinese Academy of Sciences, will launch in early 2026 to study the interaction between the solar wind and the Earth's magnetic environment. First time ever, 3-dimensional imaging there and X-ray images. Plato, which is our exoplanet explorer, which will look for Earth-like planets around sun-like stars, is also going very well. 26 cameras integrated together, phenomenal engineering and quality control to actually launch early in mid-26, early 27. And of course, Ariel will launch after that to study the atmospheres of about 1,000 extrasolar planets. So again, making that connection between the very detailed missions that we fly out into our solar system and how we connect that with the studies and the information that we bring back from distant solar systems, and ultimately studying climate change on distant planets around other stars. Sounds like science fiction. And I know if you had asked any astrophysicist or planetary scientist back in the 1970s or 80s, what chance of actually detecting a planet outside of our solar system, they would have said identically 0. And now we take exoplanets for granted. There are thousands of them detected, and these new missions will pioneer our understanding in much greater detail of the formation and the evolution of other solar systems. Comet Interceptor, I mentioned this, really is the legacy of Rosetta. It's a fantastic mission that will launch in 2028-29. We now think the solar system is larger than previously thought. We've now detected this year our 3rd interstellar interloper. So we have high hopes that Comet Interceptor will find quickly a pristine comet that has never been into the inner solar system. It will loiter round about Lagrange point 2. It will launch itself to chase that pristine comet. It will then launch a daughter spacecraft to study the comet, and we expect to then reorientate the spacecraft to study a second object. So we have our fingers crossed for some kind of exotic interstellar interloper, and Comet Interceptor will be ready to intercept. So that's giving you a kind of a whirlwind tour of our missions, everything from near-Earth heliophysics right out to fundamental physics, and ultimately with our LISA first ever world gravitational wave interferometer in deep space, studying the nature of space-time itself. Our science program is described as the backbone of ESA. The technologies that we develop with our industries, with our member states, with our science communities, and with our international collaborators really then go on and get used in other missions and really stretch our capabilities. The scientists come forward with these eye-watering ideas, and our engineers sometimes say, no, that's not possible. Well, let's figure it out. I think you'll see that throughout our portfolio. But of course, our future missions stand on the shoulders of giants. And today we're celebrating the Cassini-Huygens mission. done in collaboration with our friends in the United States. And of course, the data that we've gathered, not just the landing on Titan, but as we've heard, many of the data sets that have come back from Enceladus, the discovery there of the plumes, the first hints that we would actually be able to do some science of the underlying oceans. All of that science comes back, and our teams are using that now to design our next major large class flagship mission. And you'll hear from that in the next talk from Jorgen, who will go into detail on our L4 mission. But I think you can see this steady evolution, the need for this sustainability in our collaborations, in our mission developments, the need for the sustainability in the funding and the teams, despite the geopolitical climate, so that we can actually realize these phenomenally ambitious but important iconic space missions. As I said, Comet Interceptor will go out and do some exciting science, but what we've also done with many of our missions, because they're so well designed, because they're so well instrumented, we of course have an awful lot of serendipitous science that comes along and adds value for money. We will be observing the Atlas discovered interstellar object, and again Mars Express, ExoMars, TGO, they are already in the sky operating for many years. We understand how the instruments work, and we can actually reorientate those for science much more quickly for these serendipitous discoveries than we could invent, design a mission and launch it for a dedicated case. I wanted to give you a sense now of our solar system missions. I wanted to start at the hottest place in the solar system, of course, the sun itself. Solar Orbiter is a very exciting mission. Obviously, NASA has your Parker Solar Probe, a little bit closer to the sun, but the primary goal of Solar Orbiter really is to raise out of the plane of the ecliptic and start to see the first ever views of the poles of the sun. It was launched in February 2020, and it's already given us some very important views, not just of the surface of the sun with our multiple images and high resolution, the evolution of the sun, its magnetic fields, both in quiescence and in solar flare. And now we've started to raise the orbit of the spacecraft through gravitational flybys, particularly recently around Venus, to start to raise out of the plane of the ecliptic. So we've now got the first views. We have data coming down now. They will continue to be pulled down over the autumn and analyzed by our teams. But in July, we presented the first ever maps of the pole of the sun. We're about 17 degrees out. We will ultimately get about 33 degrees out of the plane of the solar system. And this is important because obviously the sun is now at solar maximum, and there are some theories about the change of polarity of the magnetic fields of the sun and what drives the solar cycle. So we will actually have a very, very detailed view with these data. This just gives you a first taste. You can see all of the different transitions that we have. We can do the magnetic fields, the energetics, and also some of the chemistry. And very nice paper that came out recently, actually showing the different types of solar electron flares that are coming from the sun and tracing the different energetic particle families. So again, really unpicking what's coming from the sun, how that might impact our Earth, what that might mean for our space weather predictions, and ultimately as we continue to grow our global humanity in space, this becomes a really critical underpinning for keeping our astronauts safe and protecting our space assets. As I said, SMILE will launch next year. The mission is finishing its preparation and final testing at ESTEC in the Netherlands. We will put that in storage in September, ready for the launch campaign in 2026. And it will be, this really is a legacy standing on the shoulders of giants. It's really the legacy of the cluster mission, which of course was the first identical force spacecraft to be flown to study the magnetospheric environment. The testing is complete and everything is on schedule. So what we'll do is we'll be studying the Earth's magnetic environment, what happens when the solar wind meets the Earth's magnetic shield. Of course, we have this beautiful environment that we live on Earth, and we're very protected by the Earth's magnetic field. But we really want to use this to predict the most dangerous magnetic storms, because they will have impact for our space assets, but also our ground power systems. We'll have continuous ultraviolet imaging of the Earth's aurora for the first time ever, so we'll be able to see that evolution in detail and connect that back to direct observations of the sun itself, both remote and in situ measurements. And again, this builds on the legacy from cluster, but also from XMM Newton, because it's that X-ray high energy imaging technology that is now being deployed on SMILE. And of course, all of our missions operate in the most extreme environments, the coldest temperatures, the hottest temperatures, high radiation fields, magnetic fields, particle densities. And Bepi-Colombo, I think, it really epitomizes that for us. Bepi-Colombo is a mission in collaboration with our Japanese colleagues going to Mercury. And this mission, again, is hugely ambitious, but has caused us some very difficult technical problems. We've had some challenges with the transfer of the power from the solar panels to the main spacecraft. Going into the inner solar system, of course, we have to lose momentum and we have to slow down to get into the orbit of Mercury. And that power transfer problem has really caused our teams huge problems. We don't have a root cause analysis yet. We think that it might be micrometeorite hits, and we're starting to try to understand that. But nevertheless, without knowing the origin of the problem, we still have to find a solution. The electric propulsion thrust that we have to increasingly do as we get into orbit in 2026, if you like, it's kind of a skid handbrake turn to get into the orbit of Mercury, has really challenged our teams, but we've kept it going. Incredible work. And so we're hopeful that we will reach a stable orbit around Mercury in 2026. We will then deploy the two daughter craft to study Mercury. I put the little movie on loop on the left-hand side there, which shows the real operating environment, because we always see these beautiful pictures with the black sky and Mercury there in grey, but really that is the solar environment in which Bepi is operating. So we have great measurements there as well, but also it's a hugely challenging environment to operate in. So we will learn a lot on the engineering spacecraft side. We've had some fantastic flybys in this in our efforts to actually lose momentum and get into the orbit of Mercury, and we've not wasted any of those opportunities. This is a beautiful paper that I recommend you take a look at by Beatriz Sanchez-Cano and collaborators, and it really encapsulates a lot of the Bepi-Colombo cruise science. And I'm told by our Bepi project scientists that over 200 papers and reports have already been written from the Bepi data before we've even begun the main science part of the mission. You can see here that in our third flyby back into 2023, with just 30 minutes of flyby data, we were able to map all the magnetic field structure of Mercury. And in our fifth flyby just last December, we made the first ever thermal infrared images of the surface of Mercury. There are elements and minerals there that we don't actually know what they are. So this gives you a tiny taste of the incredible science that will start to flow when we're settled into orbit. You'll have heard a lot, obviously, about JUICE. The other direction in the solar system, of course, the challenge is to gain momentum and to speed up. We had a beautiful launch in 2023. I was just a few weeks in post. We had a 1-second launch window, very complex flyby dynamics. Our wonderful flight operations teams have calculated those flybys, optimized the mission. And in fact, because the launch was so perfect, we actually saved some of the propellant, and we'll be able to have an extra rotation of Ganymede when we get into orbit there, and we'll actually be able to go a couple of hundred kilometers closer to the surface. So all of that went very well. We are, as I say, we do have quite a complex flight path. Obviously, NASA colleagues have launched their Jupiter mission. They'll have a more direct fly up there. When we've done a number of really quite daring flybys to take a shortcut through the solar system and then to most recently around Venus. But this double gravity assist through the Earth and the Moon, I think for me was really epitomizes the precision of our flight dynamics. A change by 100 degrees in direction, so almost a 90-degree turn in the middle of the solar system. And it's the first ever Earth-Moon double gravity assist flyby. As we went through this, we actually switched all of the 10 instruments on the spacecraft. Obviously, our scientists want to calibrate their instruments and understand how they might behave in the Jovian environment. And what was really exciting, and I always say this and take a breath, that we have proved that Earth is habitable so far. Long may that continue. But of course, this was important because if we're looking for signs of habitability at Jupiter, we want to actually check that we can confirm that the only planet we have proof of habitability is actually detectable by the instruments. And indeed, they are. The other thing that we did, I think the team did very modestly without making any fuss and bother, was we did a lunar mission for free. So there's a lot of very nice lunar data from the lunar bypass. And of course, the most critically important thing for the instrument teams was checking that the RIME instrument will operate the way it should when it gets to the moons of Jupiter. This was important because after we launched, the RIME antenna had a little bit of a technical difficulty. It's folded up a bit like a folded fishing rod, and of course, it didn't open up immediately. The teams were working hard to release the instrument. They were shaking the spacecraft, they were heating it up, all sorts of things you don't want to do to your beautiful new spacecraft. And of course, wonderfully, it did open up. So you can see here that the data are beautiful, and I think that brings great hope for when we get to Jupiter. And of course, we bring all of this together in our archives at ESAC here in Madrid. You can see that the archives are very popular. We continue to renovate and innovate the archives to increase the availability and the accessibility to scientists around the world. We have about 60,000 users monthly, about 135 terabytes of monthly downloads. So you can see that across all of our missions, those that are in operation and those that are legacy, our scientists around the world continue to draw the data. And as I've said, we're starting to see an awful lot of very iconic cross-mission science because of this growing suite over the last 50 years. And of course, we don't only develop missions and launch them, we also put them to sleep. This was the Gaia passivation event this year. Gaia is our billion-star Milky Way mapper. So it's not a solar system mission, but I'll show you what it's done for the solar system. This was a very poignant moment. So any of you who have been to a launch, you'll see in the top left-hand corner, that's the signal that you wait with bated breath. You've got acquisition of signal, your spacecraft is alive, and your mission is a go. And of course, for the Gaia passivation event, we did this in reverse. We actually had to put the spacecraft to sleep and put it into a safe orbit. This was quite a poignant moment, actually, being with the team. This mission has run for 11.5 years. It's been transformational to the world of astrophysics, and it's actually really hard to kill a spacecraft. And I think this is why it was so poignant in the control room, that the teams had prepared everything to make sure that it went safely to sleep. But it is quite a powerful moment in reverse. And we've sent lots of messages up from all of the scientists and the engineering team stored on that spacecraft. So if that spacecraft should ever encounter life beyond Earth, there is actually a signal left from our teams. And as I say, the main purpose of Gaia was actually to be a Milky Way mapper. It's an astrometric mission. It really builds on previous missions like Hipparcos, and this again is a really big European lead. It's a speciality that our European teams do very well. But in doing so, we actually did a solar system mission for free. And because of the astrometric precision of the measurements and the catalogs that were provided, the solar system catalog is also very powerful. Over 150,000 solar system asteroids were studied, and about 350 of those were seen to have moons, and the astrometric data are there for those. We've had 3 data releases. There are 2 more public data releases that are due to come out in the coming years, and they will vastly transform solar system science. So again, if you're not already connected to those archives, do please reach out, because I think this will again transform our understanding of the solar system. Another mission that is coming to an end, of course, is Cluster. Again, very important for our solar system understanding of the interaction between the sun and the Earth. Cluster, of course, you'll remember that Cluster 1 perished at launch, and the scientific community decided it was such an important mission that they would rebuild the 4 spacecraft. They were launched over 20 years ago, and it has really transformed our understanding of the Sun-Earth system. We have those 4 satellites in space, and of course, when the mission was first designed, it was not designed in a sustainable way, because that wasn't a priority for the communities at the time. But our instrument and our operations teams decided that it was possible to find a way to bring these spacecraft back safely to Earth. We also flew an airplane campaign so that we could study the first spacecraft re-entering the atmosphere to try to understand what the nature and the scientific importance and the impact of debris coming through. And for a 600 kilogram spacecraft, we actually detected a 100 kilogram tail of aluminium. So you can see that the sustainability of space, the ESA Zero Debris Charter that we're pushing through our supply chains, is actually really important for the safety of our planet. The other 3 spacecraft will start to re-enter this month and then over next year. And again, we're trying to study that in great detail. So we have some understanding of spacecraft re-entry at chemical level, as well as a debris and an engineering level. So in total, we have a very rich portfolio of cosmic observers and solar system explorers that are now working together in all sorts of new ways. As I said, the way our science program is built, it's founded on community consultation, it's built bottom up, and we have overarching strategies, 4 of which you can just see here. And that gives us that long-term view for our mission by mission and our individual technology development, so we don't lose sight of where we're going. We're currently completing Cosmic Vision, and we are keen to kick off Voyage 2050. Cosmic Vision, you can see the missions that I've mentioned so far. We have 3 different classes, our large flagship missions, of which JUICE, LISA, and New Athena, the world's largest X-ray observatory, due for launch in 2037. Our medium class missions, again, Solar Orbiter, Euclid, Plato, they sit in that class, and then small fast missions. And as we develop the technology, we start to be able to develop smaller missions. So Rosetta, of course, would not have been an F-class mission, but Comet Interceptor is. We are preparing the future. We have our funding ministerial this year, 2025. So every 3 years, the ministers of our 23 member states come together and set the funding for the whole of the agency. This year is critically important for the science mandatory program. We've had constant purchasing power flat funding for about 20 years. So we've continued to innovate and become increasingly efficient. But really now, for me, I think is the crunch point. We have big ambition and we have to do that in a very affordable way. You'll hear in the next presentation the detail of our next L-class mission after LISA and New Athena is to really build on our learning from the JUICE mission and go back to Saturn and really land the first ever astrobiology mission on Enceladus. We also have some M-class missions out. Currently, these 3 are in competition. These are the 3 finalists. 2 of them are solar system missions. 1 of them is an astrophysics mission. And we've recently just put a call for proposals out to our communities. We've had a huge response, and this is for the next medium class and fast class missions, and also a new class of mini F missions, which we're just exploring to see whether there is really frontier science that can be done with new technologies within these smaller cost and spacecraft mass budgets. And as I say, this year, we will follow on from 2022 when we had a record 17% uplift in the ESA budget overall, 13% in our science missions. But unfortunately, inflation actually eroded that and kept our purchasing power constant. We are hoping that we will have a very successful ministerial. We're pushing hard for that and working with our ministers. As I say, this is the nature of the proposal from the science program. Corridor 1 is to continue and to complete the delivery of our Cosmic Vision missions. And Corridor 2 is really to set the foundation for Voyage 2050. The first, of course, priority is to really set the beginning of the funding to start the real technology development for our mission to land on Enceladus, to implement the M7 mission and continue to bring in new missions into the portfolio. We are pushing very hard on this because we think it is important, and you'll hear from Jorn the actual cosmic deadline for landing. It sounds far away. It's difficult to persuade ministers to understand why they need to invest now to realize 2050, but we do need to build the future. We are at quite a critical juncture because if we don't achieve the right level of funding, we effectively are looking at an empty sky in the late 2030s, 2040s. So I think we have everything to build on and everything to play for. And really, I just wanted to again encapsulate in my final comments how far we've come in 50 years, collaborating across our 23 member states with our friends and international collaborators, in innovating the technology, inspiring the next generation, and really bringing science fiction into science fact. So I wish you a wonderful anniversary meeting today. Thank the organizers for putting this together. I think now with the current challenging geopolitical climate we have internationally, this is the time to really remember the importance of this kind of iconic space science discovery and exploration and what that means for bringing us together across national borders and whatever the geopolitical challenges are, to do something really that is so important for future generations and our understanding of our nature and our origin in the cosmos and how important it is to protect our home planet. So thank you very much.
Thank you very much, Carol, for this overview and inspiring talk. So any questions? Yes, Athena.
Hi, Carol. Thank you very much for making time. I know that you must be very busy right now, and it was a pleasure seeing you also in January in Cannes. We're having a great celebration here, so sorry you couldn't make it. We have a lot of participants from about 9 different countries. And in Europe, the US, we've had China, Japan, everybody coming together to celebrate this mission that I think you agree is exemplary in terms of international collaboration. And so just briefly, I just wanted to ask you, what is your own recipe for a successful mission with international collaboration?
Thank you, Athena. Yeah, I mean, I think there are many ingredients, and it really starts with the friendship and trust between the scientific communities. That is really where the intellectual impetus comes from. Now, that for me is not enough. Having, being a scientist, being an academic, I know obviously scientists are hugely competitive too. I think what the agencies then provide, we provide that stability. Obviously, we have our expert engineers in-house, and we work across all of these portfolios. So you have that. We're custodians of the expertise, and that can smooth out the bumps in the road. So I think you have the innovation, the creativity, and the scientific community, but obviously, scientists do other things too, like teaching or whatever, and the agencies then pull that together. At the international level, of course, we also have the legal frameworks. And so we have a very coherent structure to be able to speak agency to agency. So of course, I speak to my counterparts at the space agencies around the world. So we will have our own agency priorities where we support our stakeholders. And then when we come together at that international level, we can say, what can we do together that delivers to our priorities, that doesn't clash, but that actually adds something that we couldn't do alone. So it's that scaling of scaling. And I think, we can give some examples. So for example, for the Hubble Space Telescope, for the James Webb Space Telescope, going right back to the 1970s, when NASA were having challenges in Congress, they were having budgetary problems. It was letters from ESA saying our member states have invested, and actually international collaboration is of critical importance. And you can see that in the historical archives. And it was also true for Cassini-Huygens, that mission was pegged for cancellation. And it was really that intervention from Europe saying, no, this is an iconic mission, an actual letter to the Vice President of the United States saying you need to go ahead with this. So I think we help one another at times of crisis. One might be up, one might be down, and we smooth that out. I think we also build new capabilities. And so, for example, for the L4 mission, this will be the first time I think that ESA and Europe has the technical, the financial, and the programmatic capability to lead a major distant solar system mission in its entirety. And that for me is very important because it means that we have the stability, we have the support from our ministers, we know exactly how to do this, and you'll hear from you on how we're going to do that, informed by our scientific community. But then we reach out a hand of friendship to international agencies and we say, what is your priority? What is your capability right now? That capability might be very constrained because of political circumstances. But if you would like to bring a component, we can give a mass limit or a size limit, then you can develop your technology. It won't be on our critical path, so our mission won't be dependent on your politics, but we hold a seat for you. And I think that is really important. We don't know what will happen in the next 1, 2, 5 years. We've had to manage those challenges within the program. So, for example, the Euclid mission, which is in collaboration with NASA, major European lead on dark energy and dark matter, that was meant to be launched on a Russian rocket. And of course, when Russia invaded Ukraine, our council, which is our oversight board, severed agency to agency collaborations with Roscosmos and instructed us not to do that. So of course we have a crisis in the program then, we need a launcher, and NASA stepped in and helped us with that launch. So I think that hand of friendship, whether that's within the mission or whether it's when a crisis that comes along, so we can continue to get our missions in the sky and our scientists can extract the science that they need in a timely way. So it's nuanced, it's complex, it's great fun. And ultimately for me, I think science is the hand of friendship and peace. And I think that's really, really powerful.
Thank you, Carol. So I think